Hi everyone, this is Rachel Bartuska. I'm your teaching intern for IE 330, and the main event of this lecture is going to be talking about normal probability plots. But before we get into that, I want to spend a little bit of time going over linear rectification, what it is and how it works, and how you can use it to your advantage. Some of you may have done this before. You may have also heard it referred to as linearization, but the basic concept is we start with a nonlinear equation. We do some algebra to it, and we get a linear equation. Since linear equations in general are a lot easier to work with than something nonlinear, we can then use that to work backwards a little bit and estimate the parameters in the nonlinear equation. So we're just using math to our advantage to make something a little easier to understand, a little bit easier to manipulate, and it will tell us something about the original equation. So to illustrate that with an example, let's take the equation q equals alpha times s to the power of k. Q and s are our variable terms. So if this was some kind of experiment, we might have a column for s and there would be a bunch of points values, and then a column for q where there's an equal number of point values. Alpha and k, on the other hand, are both constants, they're both parameters, and they are both unknown. So all we have is the test data, and we're trying to get more information about it. Luckily, we can use some algebra and turn this into a linear equation, and it'll help us to figure out what alpha and k are. The first step is just to take the log of everything. And depending on how much you remember about your properties of logarithms, there is a way that we can take this, and since we've taken the log of it, it's still equivalent, but we can make it into something linear. So using the log, we can separate the two terms that are multiplied together, and we can also pull out this exponent k and put it in the front as a multiplication term. This might not look all that much easier to work with, but let's think about it logically for a second. So I said before, maybe we have some test data. S is a column of values, and Q also has a column of values associated with it. All we've done here is done some algebraic manipulation on it. So if you want to picture it as a table of values, we have a column for S, a column for Q, and then two more columns for the natural log of each of those terms. So all of these are still known point values, is really all I'm getting at. You can think of ln of q as your y value and your ln of s as your x value if you want. To talk about the parameters, on the other hand, know that we started with constants. K is clearly a lot easier to work with because it's just in the form of a constant being multiplied in front of the ln of s. And the alpha value started as a constant, and all we did was take the natural log of it, so it's still a constant now. Basically, what I've just explained is why that second line from the bottom fits the linear form y equals mx plus b, where, ln of q is y, ln of s is x, k is your m value or your slope, and ln of alpha is b or the y-intercept. So just to make myself crystal clear, I am going to switch to using the pen, and we'll go over exactly how you're going to be able to find your parameters and exactly how we can work backwards and relate y equals mx plus b to the very first line of what we started with. So say we have some kind of line. We've graphed, this is x and this is y. You can also picture this because x is exactly ln of s. I'll write that as well. That's your x-axis. And then this is also exactly ln of q. I apologize for my writing. I'm still working on penmanship with the stylus. But you get the picture. We graphed it, and this is what it looks like. Now, the alpha value is what we're going to start with, because that's the easiest to find first. If you have the information that's in this graph, this point exactly is B. You know that it's the y-intercept, it's where the line is crossing the y-axis or where x equals 0. And so now we know b, which is equal to ln of alpha. That b equals ln of alpha is our link back to the original equation, because if we know what b is and we know what ln of alpha is, then we can find alpha by basically undoing the logarithm. Just so, in case you forget, you just have to do e to the power of the logarithm and whatever's in the logarithm, and that will give you the constant value of that parameter. Now, that's the easiest one to find, and the other term is the slope. I do want to point out that this k is the only term that's not taken the natural log of. That's a common or an easy mistake to make. So make sure you know which terms have a log in front of them and which ones don't. But since we know what b is, we know all of our y values and all of our x values, there's only one variable left. So that should be pretty easy. If you find it easy, and it depends on what points are, easiest to pull out, there are many, many different ways that you can do this. The way that I think of it most easily is that m, which is equal to k, also just so happens to be equal to y minus b over x, and that should be true for any points that are exactly on your line. If you don't want to do that, or if it just happens to be easier, you can use the rise over run method, where m is y1 minus y2 over x1 minus x2, and that should give you the same answer. So to review, what we've done here is we took a vaguely gross, not great to work with, nonlinear equation. We manipulated it just a little bit, and it spit out a linear equation in y equals mx plus b form. And since that's a form that we know a lot more about and we can work with a lot easier, we were able to take a look at it, use the graph, and then find out what the parameters alpha and k are. Now, in the next video, we'll be moving on to normal probability plots.